Projectile motion. In simple word, it can be described as motion under the influence of gravity. In our day-to-day life, in our routine activities, we see many type of objects. They are moving on a curvy linear path. Suppose for the example, let's take the games. Football. When you kick the ball in football, it follows a curvy linear path. It follows a curve, then goes to the goal post, and then we announce that one goal has been done. Say tennis. Tennis is also a game in which you hit the ball with a racket. Badminton. There will be a shuttle which will be hit with the racket, and it will follow a curvy linear path in the air. Okay. One more example, one very relatable example is the game of cricket. So, in cricket, what happens? When a cricketer is there, he will hit the ball, and the ball has to go to the boundary line. It has to cross to the boundary line, and the cricketer and the team will get the points. So, once a cricketer gets experienced, he comes to know that at which angle he has to hit the ball so that it has a maximum possibility of crossing the boundary line. He knows the nature of the forces at play, and he utilizes those forces for his own benefit. So let's see, if he hits the ball, say the ball is coming with some velocity v, he hits the ball with some impulsive force, and the ball flies on an angle theta and goes directly to the boundary following a curved path. It won't follow a straight path, it will follow a curved path. But then the question comes in mind. First question, why the ball is following a curved path? Why does not it fly straight to the sky? Why curved path? This question comes. Then second question, why does it happen that after ball is in the air, it comes back again to the ground? Why it comes back to the ground? Why fall on ground? One more question can be asked, how do we know? Okay, let's say this happens that ball follows a curved path, it comes to the ground at certain point, but how do we know where it will come? Say if these distances are, how do we know, how are we certain? How can we certainly predict that this is the distance? Suppose R is the distance between the player and the say boundary line. Then how do we correctly predict that the ball when hit at some angle, at this angle with this force, will finally cross the boundary line? How? So where will it fall? How do we know this? So there is a whole science going on behind all this motion, and we can very simply understand it. And we can simplify this motion and understand this is a curvy linear path looking very complicated, but actually it is very easy motion, very very simple motion. Let's take another example. Suppose you are a soldier on the charged with the defense of the borders, and you have information. You have got coordinates of a terrorist outpost, a terrorist camp. Suppose this is a terrorist camp here. Let's say this is a terror organization's camp. Okay. Now let's make some symbols. Now you are standing at some post on the boundary, and you have been given a tank. You have been equipped with a tank. You know tank. Tank means it's a armored fighting vehicle, armored with one cannon, ballistic cannon, and along with some machine guns and all. So your CEO, your commanding officer, he tells to you that you have to destroy this identified terrorist camp, and he tells you that you have only one shot. If you fire the round somewhere else and the terrorist gets the information, terrorists get warned, then they will evacuate the camp and you will fail the mission. Also, you have the information that the nozzle, the rounds, the bullets, they leave the nozzle at certain velocity v, The cannon can be oriented in any direction, but you cannot move from your post, and because you have the coordinates of the terrorist outpost or the terrorist camp, you can simply know the what is the distance, or say distance d. You know the distance between your tank and the terrorist camp. So how do we know? How do you know that where to find out? Suppose if you fire a round straight towards aiming straight towards the camp, what will happen? You fire a round from here, velocity v, the round will fall somewhere over here on the ground. Before hitting the terrorist camp, the round will hit the ground. Why does this happen? This is because there is a gravitational force pulling the round. We cannot neglect gravity here because the rounds of a cannon are very heavy. So they will be pulled instantly towards the earth and they will fall on the ground before they fall on the terrorist camp. Okay, in this question we have taken some assumptions. One is air resistance is negligible. Air resistance is negligible. You have to neglect the air resistance. Second thing, the rounds are heavy, so gravity will pull them. G is present. When G is present, you fire the round straight, so they will fly down to the earth without hitting the terrorist. They will fall before. Suppose you have oriented the cannon at a very, very large angle. What will happen? The round, the first they will seem to fly in the sky, but soon they will fall down on the earth again. Again, you are not able to hit the terrorist camp. Then what will you do? Say you have oriented at certain specific angle theta. At theta you are orienting this cannon and you fire the round, and that time what happens? It round exactly hit the terrorist camp, not beyond the terrorist camp, because again then also the terrorist will be born, not before it, because otherwise your round will be wasted, your mission will fail. So you have to hit exactly to the terrorist point. But how do we know what this angle theta is? So the study of all these things, that how this angle theta, how this velocity and this distance d between the warhead and the target, how this distance, this angle theta and this velocities are related to each other, how we can predict the distance d using the velocity and theta, that is all will come in the study of projectile motion. Okay, let's simplify this motion further. To understand this, how we can actually simplify and study this. Let's say, suppose okay, so all these things, all these in the modern tanks and the war vehicles, all these information is encoded inside them in the targeting device, so that they just have to lock on the target and all will be taken care by the automated system. So they will take care of the range. So this distance d where you are hitting the target is actually called the range of the projectile. We will study further about it. Now consider an example. You are standing on a ground, suppose this is you, and in your hand you throw a ball. You throw a ball from your hand towards sky at an angle, say theta. At an angle theta, you have launched the ball, tennis ball, say. What happens? One of your monkey friend or one of your naughty friend, he starts running from you. He starts running such that he is always below the ball. Suppose the ball is here, so he will be here. Okay, so he is running with such a velocity that he is always below your ball. He want to catch your ball. So if we attach our frame of reference to this friend, suppose this friend's name is F, your name is A, and ball we can say is B. If F is running with a velocity V such that he is always just below the ball B, in the frame of reference of V, he will see that the ball is not following a curvy linear path. Again, imagine it in the frame of reference of the person who is running just below the ball. He is running with the ball. So in his frame of reference, ball will not follow curve, but rather it will appear to him that as if the ball is just leaving the ground, going up and again coming down. He will see the ball like that. He won't see the curvilinear path. But to the ground observer, to an inertial frame of reference, the ball will be following a curvilinear path. So what we can observe from this? If we write the formulas, suppose the ball's velocity, we can say, this friend's velocity is Vf, okay, and in the frame of reference of F, the ball's velocity, he will see a vertical component of the velocity. Let's say it is V of ball with respect to F, okay, and say the launch velocity when you are launching the ball, it's V. From the study of relative motion, say this here ball's velocity is VB. We can say that, what we can say? We can say that VB minus VF, that is the relative velocity of ball with respect to F. Vice versa, we can also say that VB, ball's velocity in ground's frame of reference, inertial frame of reference is VBF plus VF. So we have actually broken down the velocity of the ball in two components. One, VF, the velocity of your friends, horizontal only. VBF, the velocity of ball in frame of reference of your friend, is vertical. So vertical component and horizontal component. The motion of the ball, the projectile motion of the ball, is actually combination of an horizontal component of motion and a vertical component of motion, and combined, when they are combined together, they form a curvilinear path. Now if we are interested more in finding out the relations between this angle theta and all other quantities in this, so what we can do, we can just simply we can put down the natural conditions, the conditions that are existing in this type of motion. Say initially when you launch the ball, say ball's velocity is V, okay, and say vertical component velocity when you are launching the ball is, let's say it's a vertical component V1, and horizontal component, let's say V2, with this VF, and you are launching the ball at an angle theta, let's say this. So what you can write, you know one more thing, that in the horizontal direction there is no acceleration, there is no force present. Air resistance, already we have neglected air resistance. Okay, before we start solving this, let's take some assumptions. So in this question, assumption are, first assumption is air resistance is negligible. Air resistance is not present. Second assumption is the distances, whatever velocities we are considering in this, the distances are not comparable or negligible. Let's say negligible with respect to what? With respect to radius of Earth. Why is that so? Because if the distances become comparable to the radius of Earth, what will happen then is the gravitational constant, the acceleration due to gravity g, which value we are considering 9.8 meter per second square, near the surface of Earth, it would not remain constant at greater heights. And second thing, when you are considering very large distances, what will happen? The curvature of Earth will come in picture. The Earth is not actually flat, it is curved. So we want to avoid all these things. Okay. Second thing, third, we are assuming that the surface is flat. We are not taking into account the curvature of the Earth. We are assuming that the surface is perfectly smoothly horizontal and flat surface. And fourth, the velocity is considered now. The velocities are negligible compared to velocity of light, because near the velocities of light this motion actually does not remain a classical motion, it actually becomes related to quantum mechanics. Okay, this motion becomes relativity, this whole dynamics become relativistic, dynamistic, which we don't want to consider in the present course. Okay, so I think these assumptions are that's it. Yeah. Now again I will draw the diagram again over here for the better clarification. Theta, okay, and let's say now this is there. So we know that in the vertical direction there is an acceleration a equal to, okay, one more thing here. So we are considering vertically upward direction as a positive direction, rightward direction as a positive x direction. This is y, this is x, and this negative x, and this is negative y. So the acceleration, it is oriented vertically downwards towards the earth. So acceleration we will take as minus g for the vertical component of the velocity. Let's now in the horizontal direction a is 0. There is no acceleration. Let's break down these two velocity components, and we can write the equation of motion, equation of kinematic motion. Separately we will write for x direction and y direction. First let's write for y direction. So in y direction we see that vy, velocity of the ball in y direction. The launching velocity, the initial velocity of the ball is, we know, right, this is vertical component of the velocity, which is what v1 is v1, then plus at. Now acceleration is minus g, so you can write this is nothing but v1 minus gt. Okay, so vy we have calculated like this. Now what about vx, the velocity in x direction? We can say that initial velocity is v2, there is a at, t is time, time elapsed after the start of the motion, so we can say that but acceleration a is 0, so we can say that vx is nothing but v2. Velocity in x direction is always constant, that doesn't change with time. Okay, no problem, no issues. Now we know that velocity is nothing, velocity is the, what is velocity? Say vy is the change of displacement with time in y direction, so it is a dy dt. We can write vy as dy by dt. Let's see, if we write here dy by dt is equals to v1 minus gt. Now can I do like this? Can I transfer dy equal to v1 minus gt into dt, and can I integrate both the sides? Yes, why not? Let's say here it becomes v y minus y naught. Y naught is the initial displacement, initial position in y direction, and y is the final position. Then we can write here as, now v1 into dt, v1 is constant, the initial velocity, it will be a constant regarding with respect to the time. So v1 t minus, now this t dt, t square by 2, so half gt square. If I assume that y naught initial position is 0, initial displacement is 0, then I will get y equal to v1 t minus half gt square. Okay, now let's do the same thing for the vx, for the x direction. I can write that vx is nothing but rate of change of displacement in x direction, so dx by dt. Then I can write dx here, if I put here, then dx by dt is equals to v2, correct? Again same manipulation, same dx equal to v2 dt. Then we can integrate both the sides and we can write that x minus x naught equal to v2 into t. Again, if the initial position x naught is 0, we can write x equal to v2 t. We have one equation y, one equation telling us the y position, one equation telling us the x position. Can we do something like this? Okay, before we do that, now one information we have that the v1 v2 actually, in actuality, like we have done in this previous example with the ball, that actually the velocity of the ball is vf plus vf. Same thing we can do here at initial position of the ball. We can say that, what we can say, that velocity v of the ball, the launch velocity, is actually the sum of vector sum of vertical component and horizontal component of the velocity. Also, if the resultant velocity is v and we know the angle theta, so we can write the components v1 and v2 in terms of theta, and we have resolve the v in the x direction. Then we will get v2 is equals to v cos theta, okay. Then same, if we want to resolve the v in vertical direction, what we will write, this is v2, this is v1 and this is v2, right? Yeah, so v1 will be again v sin theta, so v sin theta. Now replace this v1 and v2 in the previous equations which we found as y equal to v1t plus v1t minus half gt. So I will just write v sin theta t minus half gt square, okay. And x was, so v2 t, so v cos theta into t. Now we don't need to use the vector sign because we already know the direction. This is totally, the motion is in x direction, so that is a particular decided direction, and this is specifically in the y direction, so we don't need to use vector sign here. So what we will do now, here you see, if we write it like that, x by v cos theta equal to t. Now you see, if this t, the value of time, that's here, if we input in this direction, what will happen, we can eliminate t from both the equations, and what we will get, let's see, y equal to v sin theta, now t, on the place of t I will write x divided by v cos theta minus half, now g into x divided by v cos theta squared, okay. So it will v to be cancelled, sin theta by tan theta, sin theta by cos theta is x tan theta minus half g x squared by v square cos square theta, okay. So v was the initial velocity, the magnitude of initial velocity. It will be constant throughout the motion because initial velocity are not changing, the instantaneous velocity of the ball is changing. So this is a constant, g is already constant, we have taken 9.8. so can we say that, okay, and because you have launched the ball at a certain fixed angle, so we can say that this throughout the motion, this whole quantity is a constant, and tan theta is constant, tan theta will be constant. So we can say that, suppose tan theta is a, so ax, and if we consider this as b, this is a, what you can say, minus bx square, so y equal to ax minus bx square. What is this? This is the equation of a parabola. Which type of parabola? It is an inverted parabola. So inverted parabola will look like this, and that's exactly what our motion looks like, a curvilinear motion. So we have finally found the equation of trajectory. Trajectory is the path followed by the particle. That's all for today. Welcome.